everyone! Welcome back to Knowledge Chronicle.
Imagine a giant furnace in space that turns mass into light and warmth every second, enough to power Earth 1 billion times over. Today we'll peel back the layers and explain exactly how the sun produces that energy using a process called nuclear fusion. In plain, human terms, with clear examples, so you actually remember it. Hi, welcome to Knowledge Chronicle. Let's jump straight into how the sun makes the energy that keeps life alive. What is nuclear fusion? Well, the basic idea is this. Nuclear fusion is a process where two light atomic nuclei combine to form a heavier nucleus. And in that merging, some mass disappears and is released as energy. Our key terms. First, proton, a tiny positively charged particle inside every atom's nucleus. For example, hydrogen's nucleus is just one proton. Next, neutron, a neutral particle also inside nuclei. Together with protons, they make up most of an atom's mass. Then, nucleus, the dense center of an atom where protons and neutrons live. And finally, mass energy equivalence, or E equals mc squared. Einstein's famous rule saying mass can be converted into energy. For example, a tiny loss of mass can produce huge energy because c squared, or the speed of light squared, is just enormous. Why does fusion happen in the sun's core? Well, first, it's all about extreme temperature. The sun's core is about 15 million degrees Celsius. At these temperatures, atoms are stripped of their electrons and we get plasma. Basically, a hot soup of nuclei and electrons. You know, lightning is actually a small-scale plasma you can see right here on Earth. But that's not all. There's also immense pressure. The sun's gravity squeezes the core so tightly that particles are constantly slamming into each other. So, together, high temperature and high pressure allow protons to overcome their electric repulsion and get close enough for the strong nuclear force to bind them. The sun's main fusion pathway is called the proton-proton chain. Think of the proton-proton chain as a three-stage recipe that turns hydrogen into helium and releases energy. So, step 1, 2 protons fuse. One proton transforms into a neutron, and this involves the weak nuclear force, creating a heavy hydrogen isotope called deuterium and releasing a positron and a neutrino. It's kind of like two shy dancers merging, but one swaps a shoe to fit together. Next, step 2. The deuterium nucleus meets another proton and fuses to form helium-3, which is 2 protons and 1 neutron, releasing a gamma-ray photon. That's a high-energy light particle. Finally, step 3. 2 helium-3 nuclei combine to form helium-4, which has 2 protons and 2 neutrons, and they eject 2 protons back into the pool to fuel even more fusion. Here are some important numbers to remember. Only about 0.7% of the mass involved in the hydrogen to helium conversion is actually converted to energy. But when you multiply that across the sun's enormous mass, it turns into tremendous power. In fact, the sun converts roughly 4 million tons of mass into energy every second. That's mass turned into light and heat, just pouring into space. So what form does the released energy take? Well, first, there are photons, specifically high-energy gamma rays that are produced deep in the sun's core. But you know, these photons don't just shoot straight out. Instead, they undergo what's called a random walk, scattering and being absorbed and re-emitted by particles so many times, it's kind of wild. Imagine a pinball bouncing around inside a machine for ages. That's pretty much what happens. In fact, the photon's journey from the core to the surface takes anywhere from thousands to even hundreds of thousands of years. Then, there are neutrinos. These nearly massless particles barely interact with matter at all and escape almost immediately. And that's actually why scientists can detect solar neutrinos and basically peek directly into the sun's core processes. There are 2 fusion pathways, and well, when each one matters depends on the type of star. The proton-proton chain dominates in stars that are the size of the Sun, or smaller. On the other hand, the CNO cycle, which stands for carbon, nitrogen, oxygen, is another fusion chain that uses heavier elements as catalysts, and it becomes important in hotter, more massive stars. So, to put it simply, larger stars use a different engine under the hood, but they still rely on fusing hydrogen into helium. Why does fusion keep the Sun stable? It all comes down to something called hydrostatic equilibrium. Gravity pulls inward, while the pressure from hot plasma and the energy from fusion push outward. These two forces balance each other, producing what we call hydrostatic equilibrium. It's kind of like balancing a beach ball underwater. Gravity pushes in, the buoyant push pushes out, and that balance is what keeps things steady. The Sun has a finite supply of hydrogen in its core. Over billions of years, the core runs low on hydrogen, fusion slows, and the star evolves into a red giant and later other stages. Think of the Sun's core like a huge fuel tank. Right now, it's comfortably mid-journey, about 4.6 billion years old, and expected to keep shining for roughly 5 billion more. So, what real-world evidence have we actually observed? First, solar luminosity. Precise measurements of the Sun's brightness match the expected fusion power output. Second, solar neutrinos. Detectors on Earth measure neutrinos from the Sun, confirming nuclear reactions are happening right now in the core. And third, stellar spectroscopy and models. Observing other stars at different stages confirms fusion theory explains stellar life cycles. Why does fusion matter beyond just understanding the Sun? Well, for one, there's the energy potential here on Earth. Scientists are trying to replicate controlled fusion to create a clean, nearly limitless power source. For example, experimental reactors like tokamaks confine plasma with magnets, trying to recreate the Sun's core conditions. And then, in terms of cosmology and element formation, fusion in stars builds heavier elements, seeding the universe with the material needed for planets and life. So, the Sun's power comes from billions of tiny nuclear reactions happening every second in a super hot, super dense core. Protons fuse, a small bit of mass disappears, and enormous energy appears, as light, heat, and streams of particles, powering everything on Earth.